Welcome to the MLOps Live Webinar series. We're going to get started in just a minute. We're just waiting for a few more folks to join us. Okay, welcome everyone, and thanks again for joining us. This is our 19th session of the MLOps Live webinar series, and today we're going to be talking about the move from AutoML to AutoMLOps. We'll talk about automated logging and tracking of machine learning. And it's my pleasure to introduce Yaron Chaviv, co-founder and CTO of Iguazio, and Guy Lecker, ML engineer at Iguazio. They're going to be discussing the challenges of operationalizing machine learning, what it means to move from AutoML to AutoMLOps, how to automate different data engineering tasks to make the whole data science process more efficient and more effective for your data science team. They're also going to be showing two short live demos. One is a machine learning use case. It's a breast cancer classifier with sklearn. And the second is a deep learning use case. It's a mass detection classifier. During this webinar, we're also going to run two polls. We'd love for you to participate. It helps us make these sessions more valuable for you. And we'll be recording this so that we can send you the link to the recording after the session. We'll also have a live Q&A where you can ask us your questions, and we'd love to respond. At this point, I'd like to pass it over to Yaron to get us started. Yaron, please.
Okay, thank you, Sahar, and thanks everyone for joining the webinar. Before we are going to dive into the solution and how we automate MLOps using some of the tools that we've developed, let's talk about the problem. So what you see here in the diagram, this is a traditional way people develop machine learning model. They have some source for the data, a data warehouse or some data lake or just a bunch of files. They're taking that, they're doing all sorts of data preparation on it, training a model using interactive experience in a notebook or using some managed AutoML service, evaluating the model, assessing how well it is, how accurate it is, and so on. And finally, we generate a model, which is an endpoint that needs to go to production. This is the traditional way. In reality, we're going to see it's much more complicated. But still, even within this process, users want to be able to track every experiment they do. They change parameter. They want to see how the parameters will impact the model behavior, the model accuracy, and so on. So there are many different tools today in the industry that allow you to log the results of your model. So, there's weights and biases and ML flow and maybe other solutions. So every time you'll run your experiments, you'll have to add some instrumentation to your code in order to be able to track. This is sort of the first version of trying to automate some of the work in machine learning. It's really more focused on the logging, on being able to reproduce the results that you've done, going back in time based on the parameters that you've used or the data that you've used, ability to visualize and compare. It still does require manual intervention in your code to be able to monitor and track your solution. But those solutions that essentially track and compare experiments, on one end, as we discussed, they add a lot of manual work to your code to be able to log. The other challenge, they don't address the full operational life cycle of machine learning. In reality, data doesn't just land in a bucket or comes as a CSV or Excel spreadsheet. It comes from live data system, from data warehouses, from live streams, from HTTP and API endpoints. The training is not done manually. It's essentially done automatically over microservices in a distributed fashion to be able to process a lot more data. And the results have to be stored in a way that they could be used in production. So we need to have things like model registries and model artifacts and also The production line is rarely a single endpoint. It does have a sort of a pipeline of gathering data and enriching data, processing the model results, reacting on the data. And there's also a lot of monitoring. So this requires a lot more effort when we're trying to operationalize our machine learning. All those little arrows that you see here on the slide are essentially glue logic. These are code pieces that you need to write and implement. And what we're trying to achieve with AutoMLOps is essentially eliminate as much code as possible. So you would essentially write your code in the original way that you intended and add some of that glue logic that is required for all those different pieces in automatically and inject it into your solution. So what are other things we want to be able to track, before we move into full automation? We don't want to be able to track more and more aspects of our machine learning workload. So we want to be able to auto-tune, not just track and visualize. We want to be able to run essentially the same job and let the system automatically try different permutations and find the right and best model. So this sometimes also refers to as AutoML, running a set of experiments and seeking the optimal results. So this is another thing we can try and automate. There are other aspects of being in the production of legal or governance or explainability, sometimes referred to as responsible AI, is the ability to control the entire process, see what data we trained on, what were the results. So later on in the process, if our model misbehaves or produces problematic results, we can go back in time and understand what happened, also control and govern the process of deploying our machine learning. Many cases, we're not just running training, we're running a set of pipeline operations. We're preparing the data, we're creating the model, we're conducting testing, we're trying to deploy. So we want to be able also to build those pipeline in an easier way. So by tracking or recording results of one step and moving them to the other step, that makes life simpler. Also machine learning, especially if you want to try it in many different permutations, is very resource and CPU intensive. Sometimes you also use GPUs, which are better for especially deep learning workloads. And we want to be able to analyze that we're actually using the resources properly. We're not abusing resources. We don't have bottlenecks that could be solved by writing the code slightly different. So we need also to be able to profile our code and optimize our code. And finally, we also want to be able to collect different data elements and metadata elements automatically. So for example, when we're deploying a model, when we're storing and registering a model, we record all the production-related aspects, what data it was trained on, what are the statistical patterns, what are the properties for deployment, etc. So when we're running the deployment, we have all that metadata packaged with the model instead of having to generate that manually. So this is just some of the things that we need to add. We can do it manually, but obviously a better solution would be to automate this. So in general, what does it mean execution tracking, which is part of this AutoMLOps is the tracking, is the ability that every time you run your code, your machine learning job, whether it's a data preparation or training task, be able to record everything that goes into it, be able to reconstruct the source code along with all the package dependencies, and finally, record the outputs of that job. So every time we record the inputs, we record the outputs, we record the environment, what kind of Python packages you installed and so on. We know how to go back in time and try and reconstruct exactly the same execution. This is a general idea about execution tracking, which is again part of that. And when we're talking about tracking, it's not just tracking the training job, because this is a typical machine learning pipeline where we grab code from some source control, we grab data from a feature store or some data source, and then we do data preparation. So the output of the data preparation becomes the input of the training, and so on. The output of the training becomes the input of the testing and validation. So we need to be able to pass data, parameters, results, and so on between the different steps of the pipeline. And this way, it will automate our entire flow. If we also track that data, so we get two things in for one. On one end, we can pass data along the steps of the pipeline, but we can also track on retrospective what were parameters used in each step of our job. This is something which require essentially a database or a common API and metadata model, so we can pass those things across the different steps of the pipeline. Now, beyond the tracking, which we just spent a few minutes on, there's also ability to provision and automate the work. So it's not just about tracking. We want to be able to record the things that we do or inject parameters into our tasks. We have to start adding, as you see here, examples how it's done in like MLflow or other solutions. We have to start adding parameters to our code, making sure that we can inject different parameters for hyperparameter testing, or we need to inject code for logging different metrics, different parameters into our code. This is adding additional development work. We have to be able to integrate whatever we're doing with the Git, with CI/CD system, with reporting systems. So if we want to report into different systems like TensorBoard, we'll see in a minute in the deep learning use case, we have to add code to export our information into TensorBoard. In many cases, we want to be able to train the jobs horizontally, to train the models using multiple computation elements, not in even one. This is another place where we have to add hooks and sort of partition data or partition the model in order to be able to distribute the workload. Can we do it automatically? We're going to see the answer in Guy's demo in a minute, how we can essentially try and distribute the workload without writing additional code. Something very significant when we're working in the cloud or in distributed systems, where is the data? It's not local in our computation element. Sometimes it's in the cloud. Sometimes it's in a database. So we need to be able to launch the jobs and essentially point to data in the cloud or in some database, and then store it again in that remote location. So one option is starting to learn all the different APIs for object store, for databases, etc. Another thing is to let the system automatically persist data in the right locations, or automatically fetch the data before your job actually starts running, instead of you having to handle it. And again, there are many other aspects that could be automated, like gathering the data and metadata for the operational aspects, security, hardening, protection, and so on. And also something very significant is the notion of versioning. When we deploy something, we want to have a version tag associated with it. So if we want to roll back, we can go back to a previous tag and so on. So the way that we've addressed those things is using two open source technologies, which are very successful: MLRun, which is about MLOps orchestration, and Nucleo, which is a serverless processing engine. So essentially, Nucleo allows us to automate the deployment of workloads. MLRun allows us to track and orchestrate the entire process. How does MLRun work? MLRun is comprised of 4 individual pieces, the first, which are all running on top of serverless technology. And the first piece is being able to prepare and generate the data using the feature store. The second part in MLRun is all about automating the workflow of generating the model across multiple steps, grabbing the data, preparing, training, testing, deploying, and so on. The third part in MLRun is about the online serving pipelines, where you can have a pipeline with multiple steps. Again, data enrichment, data preparation, data validation, serving, actions, metering, and so on. And the last piece in MLRun, is the model monitoring or data monitoring. So all the data from the production system goes into an analytical engine that collects, aggregates, alerts based on all the information, and writes back the production data into the feature store for use in later use cases. MLRun has a very rich SDK and API and can work with many third-party systems, whether these are notebook engines, CI engines, AutoML frameworks, and so on. So again, MLRun has those 4 pieces. We're not going to talk about all those 4 pieces. Go to MLRun documentation and tutorials, and you'll see more on that. We're going to focus mainly on the development flow of your model. So the underlying thing in MLRun that everything else works on top of is this notion of serverless function architecture. What does it mean? It means that I can take a piece of code and push a button or call an API call that will take that piece of code and turn it into a fully managed and elastic service. How does it work? This code gets sort of compiled, gets wrapped into sort of a container along with all its dependencies. There are multiple types of engines in MLRun, like Spark and Kubernetes Job and Nucleo for real time, and Horvath for deep learning that we're going to see in a minute, Dask and so on. So different runtimes will address the scaling of our workloads in a different way. And also there's an underlying set of resources that are controlled by this serverless engine, how many CPUs and GPUs, et cetera, we need to allocate to our job. And monitoring or controlling that. In those serverless functions, there's a cool thing is that they're running in a sandbox, that everything goes in, everything goes out is recorded. So all the tags, the labels, the parameters, secret credentials, data, etc., are pushed into your code automatically. You don't need to deal with data movement. And once your job finishes, it essentially logs all the results automatically, matrix data, operational data like logs, CPU, GPU usage, and so on. All that is tracked automatically. You don't need to do any work for that, and we're going to see that in a minute. And how does it help us is because in the traditional process, when you're developing a piece of code, you have to pass it to ML engineer. The ML engineer will take that code, automate it, build the managed service around it in Kubernetes. That's a lot of DevOps work. Finally, when you did that and someone wants to build a pipeline which comprises of those different steps, training, testing, data preparation, so on, you need to build a pipeline that comprises of those individual steps. So this is another task which is done today manually. And finally, someone needs to monitor all those different activities. So that's another manual task. In MLRun, it's all automated. So when you build your code, one click or one API call, you move it into a microservice, a fully managed microservice. This microservice is also a component in a bigger picture. So you can just take a canvas and build those individual steps into a pipeline and deploy the pipeline as a whole. All those different functions in MLRun are essentially auto monitoring. They have instrumentations to monitor everything at the different layers. So you have codeless monitoring. Once you start putting those into production, you'll see dashboards, you'll see the activities, and so on. And you can use those activities as a feedback loop for things like retraining or for exploring the production data or analyzing the production data and retuning your model and redeploying it again. So this is the general idea. This is just a few examples that Guy is going to dive deeper on. But let's assume that we want to build our own training function. Nothing special. This is just a standard code that we're developing. The only line that we need to add to our code is the one that you have here, which is essentially all this AutoMLOps in a single line. So we write our standard function. We have some signature where we can use above. We don't need to use all those arguments that you've seen in my slide before. This is automatically going to be analyzed, and MLRun will learn this function automatically. And what this single line adds to our system is all those things that you see here, is automatically logging the artifacts, the different matrix based on the framework you're using, saving the model along with its metadata as a package, auto scaling your workload, all those different things that you see here. They're also, if a data scientist writes the code without this single line, the only thing he needs to do to gain all those features that could be months of engineering is just adding a single line. So how does it work? Once I created this function, this trainer.py function that we've seen before, I could just turn it into a microservice using a single API call, code to function. And then when I have this serverless function, I can just say run. It will execute this function, or I can execute it with different parameters like data or other parameters. And now if I want to run the same function with a dozen different permutations and different parameters and choose the best model, the only thing I need to do is just pass hyperparameters to it instead of regular parameters, and it will execute the same job with all the different permutations and select the one with the best accuracy that we specified here. So we can essentially automate the tracking and automate the execution without doing any coding. And finally, this is an example of all the different matrix that are being collected automatically. Remember, in our code, we didn't do any logging, any instrumentation, any packaging, just added one line of code. And this is used in a bigger picture. You can essentially build a multi-stage pipeline, that gets triggered automatically and run multiple stages. Those artifacts or those data elements will be passed along the different steps of the pipeline. You could go into MLRun, track it, and see the progress, see the artifacts. You can also see all those things in your Git systems or third-party open source solutions. Also, those functions in the marketplace, once you've built them, you can just put them in a marketplace or put them in a database and drag and drop them into your pipeline. So you don't have to build all those steps all the time again and again. You could essentially code some of the components once or use the built-in library of functions and use them in your system. And what you can also see is that MLRun is an open system. So everything we track, we don't only track in MLRun UI, we can export all the telemetry information that we track into the Jupyter Notebook, TensorBoard, Git systems, Kubeflow, even Slack, and other systems. So again, you can choose which tool you want to use for monitoring and tracking your machine learning workloads. So with that, let's move to the poll question, and later on, Guy will show us a couple of demos, the machine learning demo and a deep learning demo. Thank you.
Thanks so much, Yaron. So we're just going to pause there for a quick poll. We want to hear from you. What type of data do you use in your models? Is it tabular? Is it text, images, video, audio, or multi-format? It's demo time, so I will hand it over to Guy.
Okay, thank you, Sar. Thank you, Yaron. Hi, everyone. Just a moment, let me share my screen. Okay. So we will start by demonstrating two demos, one for machine learning and one for deep learning. Basically, we will showcase what you just seen in Yaron's presentation, the quote unquote magic one-line solution called Apply MLRun. So let's just dive in right now. As you can see, I'm in the MLRun documentation site, and we'll go through on this little tutorial. So in this tutorial, we will train a breast cancer classifier. We will start by importing MLRun and create a project using the MLRun get or create project. This is, you see, it's loaded a project. And now there is an explanation about the apply MLRun, which you already saw. And this is our code. So the code is really straightforward. It's a training function. It's get some configurations like estimators, max depth, learning rate, and the dataset. And what is most importantly here is that this function. So apply MLRun takes the model we just initialized. It takes the model name, it takes the X test and Y test dataset we just split here, and it will wrap around the sklearn framework and will produce automatically some useful artifacts like feature importance, for example, and it will log the most like common accuracy metrics. Of course, the function is very configurable and customizable, and you can just do your own and even write your own artifact if you would like. So here you call model.fit, which is this sklearn API again. And now we are creating the function. This is the trainer.py, which we are creating here. Excuse me, it's here. It's the right file in Jupyter.
Guy, maybe you can maximize the window. You have the 3 lines. So to hide the menu on the left, the other side.
Yeah. Okay.
Great. Thank you.
And okay, so now we have our function, and it's time to run it. So we will take the breast cancer dataset from sklearn datasets, and we will save it to a CSV file. And then we will run function and pay attention to this keyword argument, local equals true. That means we will run the function locally on our interpreter. So this is, as you can see, excuse me, we'll just move the camera. This is the results. You can see here the accuracy metrics, the artifacts, and the model artifacts. And here you can see we just took the run object and call output. So we have all the outputs, and we can even in Jupyter, we can just do call artifact, write the name, and hit show. And then we will see the plot the artifact of feature importance, for example. Another cool feature is that if you would like to send over a model you just trained to a colleague or even between projects, you can simply get the model artifact and then just hit export, and it will export the artifact. Of course, you can do it on every type of artifacts, dataset artifacts, etc. And it will simply be exported, and you can later import it into your project. So here we have the hyperparameter tuning. Now we will need to have multiple workers to run the hyperparameter tuning job. So in this case, we will need to log the dataset so it will be available on the cloud. So we will hit the project log dataset. We are giving it a name, giving it the source. And now all the workers can access it without a problem. We will take the URI of the artifacts we just created and send it over via the inputs of our function. The hyperparameter, we will just use the estimators to 10 to thousands and the learning rate and so on. And by selector, we will use the maximum accuracy for the best model. Now, once we run it, we will see in the UI, we will be able to see all the runs, all the results that were produced, and even the winner with this little ribbon here. And we will have even parallel coordinate plots, which you can see what yielded the highest accuracy in a much more visible way. Again, that's the outputs of the best model. And well, that's stuff for later. You can see about serving functions later on or in the MLRun docs for yourself. Now we'll go through the second demo.
Anyway, it's important to pause for a second and highlight that you've seen how many things you got for free. You got a lot of visual aspects. You got the models being logged. You can compare models. You can upload models. All the automation around hyperparameter tuning, all of that without adding more than a single line. We just added one line, and all the automation of those aspects of operations were deployed automatically. We took our code, we passed it into the cloud, we ran it on the cloud in a distributed way, all of that without adding more than one line.
Yes, exactly. And now we will move to the mask detection demo. In this demo, we will be using TensorFlow, although we are supporting PyTorch as well. Same for the machine learning frameworks. We are supporting gradient boosting like XGBoost and LightGBM and so on. So in this demo, we will be using a dataset that, I'm sorry if I'm butchering her name, Prainia Bahadari, and the code itself is being taken from PyImageSearch. Now, the reason we took the code as it was is just to showcase how easy it is to wrap it around with MLRun and just run it, and then you gain all the automatic logging and experiment tracking. So the code is available here. You can see here, I just reorganized it so it will be more visible. We have the get dataset, which will simply go on the images and get the dataset, reprocess and enable to MobileNet. The model itself is, as I just said, it's based on MobileNet. It is using transfer learning. And here is our training function. So the training function is very straightforward. We get the dataset, we get the model, and now we simply use apply MLRun. Apply MLRun will wrap around and insert multiple things, so you will be able to view all the loggings in MLRun and TensorBoard if you like. We initialize an optimizer, we call compile, and then we simply call fit. That's all the code, very usual stuff, just this line that is the changes we inserted. So now, let's again set up the project. I'm giving it the name mask detection. Again, get or create project like we did before. And now we will download the data. To download the data, we will import a function called Open Archive. We are importing from the function marketplace. You can see here, I just hit MLRun function, then I get the function. I can call doc, and I will get the documentation. You can see here the URL, the parameters it expects, and now we will run the function. So we will have the data set that is sitting in our Wasabi, and we will simply call run. Now, run will call the function we just imported, and it will download the data set to here. So you can see here the data set, you can see here all the images. For example, let's see this image. Here you go. So now in this demo, as I said, we support both PyTorch and TensorFlow. We will focus on TensorFlow. So we are choosing TensorFlow, and now we will create a function. We will use code to function on our code. It's this file, training and evaluation.py. That's the file. We will give it a kind of job, and now all we have to do is simply run it. So when I run, I give it the batch size of 32, learning rate, and 3 epochs, and the dataset path to take the images from. And the local now is false. So it will deploy the pod with that will train our model, and I will be able to see it here. So this is the MLRun UI. You can access it from here. You can simply click this link. And here I can see all the inputs, the labels. So that's my username, client version, the results. So I can click here, I see the results. The learning rate is automatically being tracked. I have the training and validation loss and accuracy. And I have all the artifacts, for example, training accuracy. Let's click it. And I can see here, I have 3 epochs and the results it yielded. Now, if I were, to evaluate my model, I have an evaluation function. So the evaluation function takes a data set, and then we need to call evaluate. So in order to evaluate the model, we need, like I said, the data set and the model, of course. So I get the model path. It will be a URI of the artifacts we just logged, and we can access it via the apply MLRun. So I click apply MLRun, take the model path, and then I get something we call a handler. The handler is an API that is used for logging, saving, and loading a model. So apply MLRun automatically detects the model path is of a URI, it loads it and returns a handler, and then I can access my model via the model attribute. And then we simply call evaluate. It's the same evaluate of a TF Keras model. And because we use the apply MLRun, evaluate will automatically log the evaluation and update in the UI. Sorry, waiting for the Zoom to disappear. Okay. So now, if we were to run a much heavier task, like, for example, I want to train on a much bigger data set. I want to train on a much bigger model with multiple parameters, weights, and so on. I will want to distribute my training. What does it mean? I mean that I will train on multiple GPUs and on multiple machines. So for that, there is a framework called Horovod, and MLRun is using Horovod seamlessly, and it will detect that it should be using Horovod automatically. How it is being done? So we will create the function again from the same code, but this time notice the kind is an MPI job. Horovod is running on top of an MPI, open MPI. And now I will, of course, there is more addition stuff. If I want to use GPUs, here it's set to false. If I want to use the GPUs, all I need to do is just take the function and call GPUs and assign the GPUs I want. For this demo, I just hit false, and I simply deployed 2 replicas that will both use 2 CPUs. And now I simply hit run. Now you can see I ran it and it's done training, but keep in mind that I didn't change the code. It's the same code you see here, it's the same training function, but because I just hit the OpenMPI kind, sorry, I just set the OpenMPI as the kind of the function, MLRun is automatically knowing to wrap around the code with Horovod, and it will train on the amount of replicas you just configured in the function. So as a bonus, we can see the TensorBoard here. And you can see here I ran twice. I ran the mask detection. You see here the project and my username. And you can see 2 runs. One is the normal training run, and one is the distributed training run. And what's cool is that you can see here, the orange is the regular training, because you can see it has more iterations. And the blue one is the Horovod one, because we use 2 replicas. So we had 2 workers, and so the dataset was split between them 2. So we have half of the iterations. In addition, it's not like it's not the typical TensorBoard. It's connected to MLRun via the text API. You can see here summarizes and linking to MLRun itself. We even have the hyperparameter tuning table, so you can run multiple jobs and see which yielded the best results. We support all the usual stuff. We have the models graph, so on, and that's it. Yaron, would you like to add something?
No, thank you, Guy. And here, what we see, in addition to the logging aspect, we've seen how we can also run at scale without any additional work. And again, thank you, Guy, for everything.
Sure.
Great. Thanks again for that, Guy. So there's a couple of ways that you can get started with MLRun. Yaron, would you like to say a couple of words about the 3 ways to try MLRun?
I think the best is to just go into the MLRun docs site or just type mlrun.org. There are a bunch of tutorials and installation instruction. You can install MLRun locally using Docker. If you want to do things a little higher scale, you can use the Kubernetes. There are associated instructions in the documentation, or just go to Iguazio and we have a fully managed solution. You could get a free trial access within minutes. And there are also tutorials in Katacoda, and there are a bunch of demos. All the things that we demonstrated is code that is in GitHub and could be accessed by anyone.
Excellent, thank you. And we do invite you to try this. We'll also share the links with you in the chat. And now we'd like to ask you another poll question. We're interested to hear how you deploy your ML models today. Do you either don't need to deploy models? Of course, that's the first option. Do you use open source frameworks? Do you use off-the-shelf enterprise solutions? Or are you looking for a good solution for model deployment? Please let us know. That's a wrap on this session of the MLOps Live webinar series. Thank you so much for joining us. There's lots of additional MLOps resources for you on our website. Just go to iguazio.com/MLOps. You can see previous sessions of this series where we've hosted industry experts from S&P Global, NVIDIA, AWS, Microsoft, GitHub, and many, many other enterprises. You can read our MLOps blogs on topics like experiment tracking, like building ML pipelines over federated data, using real-time feature analysis, using feature stores, and so on. So we do invite you to check those out and let us know what you think. And we also invite you to join our community. We have a growing community of data scientists. It's called MLOps Live, just like this session. And it's on Slack. So we'll share the link with you in the chat now. And we'd love to continue the conversation with you over there. At this point, I'd like to thank Guy and Yaron for joining us today. Thanks for sharing all of this information with us. And we look forward to seeing you on our upcoming webinar. Thanks everyone for joining.